Gears. Although very simple in nature, they're vital to the functioning of many everyday machines. These include cars, watches, clocks, bikes, fans, electric tools, and even washing machines. However, even though they're part of such a large variety of appliances, their role and importance often go unnoticed. So how do these simple machines really work? Well, first off, it'd be important to understand what a gear even is. The gear is a simple machine that is defined as a cylindrical or cone-shaped surface with equally spaced teeth that allow the gear to mesh with other gears, forming a gear train. This definition is pretty broad, and for a good reason. There's actually a much larger variety of gears than most people would imagine, with different applications for each. The most commonly used type of gear, and the one that's most recognizable as well, is the spur gear. The spur gear is that classic looking gear that you would probably imagine when thinking of gears. Based on its shape, it's classified as a cylindrical gear, and when trying to make a system of spur gears, they would be placed parallel to one another. As you can see in the picture, this would make the most sense as their teeth are straight, so parallel connections would allow multiple spur gears to mesh. Some devices that include spur gears include washing machines, dishwashers, blenders, screwdrivers, and wind-up clocks. Now you may be wondering why spur gears aren't found in cars if they're so popular. The reason for this is because each time the teeth on spur gears mesh, they cause an impact and collide with one another, producing a lot of noise and vibrations. These conditions would not be ideal for machines like cars. So with the basic understanding of spur gears, let's see why gears are considered simple machines. The main purpose of gears is to transfer energy from one component in a machine to another, but besides simply transferring energy, the arrangements of these gears when meshed together, which forms a gear train, can also lead to increases or decreases in the torque or speed that is outputted. But wait, what is torque? Torque is defined as the force applied to an object that causes it to rotate on its axis of rotation, or also known as its pivot point. In other words, it is a twisting force that causes an object to rotate. The equation for calculating torque is T equals to F sine theta r, where T is equal to torque measured in newtons over meter, which is equal to force that is perpendicular to the distance r measured in newtons, and r, the distance between the axis of rotation and the point where the force is applied, measured in meters. When looking at this equation, however, there's probably a few things you might have noticed. First of all, it looks a lot like the equation for work. However, torque is proportional to the component of force that is perpendicular, not in the same direction. Secondly, it is the fact that variable r is in the equation is equal to a distance between 2 points, not some distance traveled. As r is proportional to torque, does that mean that a small force that's applied far away from the axis of rotation can produce a lot of torque? Let's explore this idea using the following diagram. Suppose you have two wrenches that are different lengths and have their axes of rotations at A1 and A2. You apply forces F1 and F2 on both wrenches at points P that are perpendicular to the wrench. The distance between points P and axis of rotation A is R1 and R2. Given these values, calculate how much force must be applied on wrench 2 to produce the same torque on wrench 1. Plugging the values of wrench 1 into the equation for torque, we get T1 is equal to F1 sine theta R1. T1 is equal to 18 newtons multiplied by sine 90 multiplied by 0.15 meters. T1 is equal to 2.7 newtons. Knowing that T1 is equal to T2, T2 is equal to F2 sine theta R2. T2 over sine theta multiplied by 0.30 meters is equal to F2. F2 is equal to 9 newtons. As you can see, only 9 newtons of force on wrench 2 is required to produce the same amount of torque as wrench 1. And if instead of 18 newtons were applied on wrench 2, then the torque produced would be double that of wrench 1. This is all due to the differences in where the force is being applied relative to the axis of rotation. The idea of using less force to output more at the cost of speed or distance, among others, is called mechanical advantage. Now that we learned a little bit about torque, how can we determine actual values of the outputted speed and torque in a gear train when they've increased or decreased? Well, we would have to utilize what are known as gear ratios. Gear ratios are based on gear trains, specifically the positioning of the actual gears. As gears can be arranged in multiple ways, gear trains can have multiple gear ratios. In order to make gear trains easier to analyze, however, certain names were made to label the gears. These specific names are given depending on the positions of the gears. In a simple case of two gears, the gear which has a force applied to it is called the driving gear. The second gear, which only rotates due to the driving gear, is called the driven gear. Going back to cars, the gears connected to the motor would be the driving gears, whereas the gears connected to the wheels would be the driven gears. These terms relate to the gear ratios as they're actually used to calculate them. First of all, gear ratios are equal to the number of teeth on the driving gear to the number of teeth on the driven gear. From the gear ratio, you can classify the gear train as either having a gear reduction or being in overdrive. If the actual value of the gear ratio is lower than 1, meaning the driven gear has more teeth than the driving gear, the gear train will have a gear reduction. If the gear ratio is greater than 1, meaning the driving gear has more teeth than the driven gear, the gear train will be in overdrive. These terms will be explained further in example problems, but before we get into these examples, there is an important concept that you need to understand first. Simply put, speed and torque are inversely proportional when being outputted in gears. If speed is increased, torque must be decreased. Conversely, if torque is increased, speed is decreased. With that in mind, let's go over the scenarios. Suppose you have two spur gears meshed together in an ideal environment where no energy is lost from the system due to friction. The first gear, which has a force applied to it, meaning it is the driving gear, has 8 teeth, while the second gear, the driven gear, has 16 teeth. Using the formula for gear ratios, which is the number of teeth on driving gear to the number of teeth on the driven gear, we can determine that the gear ratio is 8 to 16, which can be simplified to 1 to 2. As the gear ratio is less than 1 due to the driving gear having fewer teeth than the driven gear, the gear train has a gear reduction. But what does that truly mean? Well, we already know that the energy is being transferred from the driving gear to the driven gear without energy being lost. However, these gears are obviously different sizes. Each time the teeth of the gears collide and transfer energy, the driving gear, which is smaller, would rotate a greater distance than the driven gear due to the having fewer teeth. To explain further, if the whole gear is equal to 360 degrees, the angle separation between each tooth would be greater in the smaller gear than the larger gear. So it would be able to complete the 360-degree rotation after fewer teeth collisions. How much faster, you ask? Well, if we look at the gear ratio of 1 to 2 and apply our new knowledge, it tells us that the driving gear should be twice as fast as the driven gear, or in other words, the driven gear has half the speed. Consequently, if the speed of the output is being halved, and the speed and torque are inversely proportional, then that means the torque produced by the driven gear should be doubled. As we mentioned earlier, if the output torque is being increased at the expense of something like speed, this would be called mechanical advantage. So to recap, in a gear reduction, where energy goes from a smaller gear to a larger gear, torque will be increased, but speed will be decreased, which translates to gear reductions having a mechanical advantage. But what if, instead, the larger gear was instead the driving gear and the smaller gear was the driven gear? How would the output speed and torque change? We already know that the gear ratios are equal to the number of teeth on the driving gear to the number of teeth on the driven gear, so in this case the gear ratio would be 16 to 8 or 2 to 1 since the driving gear now has 16 teeth and the driven gear has 8 teeth. The gear ratio would now be equal to 2, which is definitely greater than 1, meaning the gear train would be in overdrive. Once again, no energy is lost between the driving gear and the driven gears, but they are different sizes. By looking at the gear ratio of 2 to 1, we know that the driven gear will have twice the speed of the driving gear. We also already know that the speed and torque are inversely proportional, which means that the output torque must be half of the input value in order to compensate for the double speed. To recap, a gear train in overdrive occurs when a larger gear drives a smaller gear, leading to an increased speed output but a decreased torque. But how can we bring all these together? Well, let's apply them to a real-life model, a bicycle. Our bicycle has 3 different sized pedal gears, which are the driving gears, and 7 different sized wheel gears, the driven gears. Regarding the pedal gears, going up gears, for example from gear 1 to gear 2, increases the radius and the number of teeth of the gear. However, for the wheel gears, the opposite occurs. Going up gear numbers, for example from gear 6 to gear 7, decreases the size and the number of teeth. This means when you're changing gears while riding a bike, you're really changing which pedal and which wheel gears are being connected, which changes the gear ratio. Now let's get into some specifics and analysis. The highest gear ratio, meaning the greatest overdrive, would be achieved when the pedal gear is on 3 and the wheel is on 7. This would produce the greatest speed output compared to the input with the least amount of torque as shown in the video. This gear setup would be most ideal when the bicycle is already in motion, as you no longer require much torque to start the bicycle. On this bike, the smallest pedal gear is the same as the largest wheel gear. This means it is impossible for the gear train to have a gear reduction, as the gear ratio will be always greater than or equal to 1. The lowest gear ratio would be achieved when the pedal gear is on 1 and the wheel gear is on 1, producing a gear ratio of 1 to 1. This gear ratio in an ideal world would mean that the same torque is being inputted as it is also being outputted, and the speed of the rotation would be unaffected. This is ideal when you first start pedaling on a stationary bike, as the output torque is not being decreased significantly except by friction, so you won't need to exert much force to get the wheels going. Thanks for watching our video about gears, mechanical advantage, and gear ratios.